Let's see if I can fix that.
Okay, can you hear me now? I think I fixed it. Okay. You should also know that this is for my other class. So this isn't for Chem 100. This is Chem 103. But I'm glad you're here. It's the same material. It's just we're doing it a little bit differently. Okay, let me go back to the beginning then, because nobody could hear me for the first part. Thank you very much for letting me know that. Okay, so starting over. What I was saying for a while with nobody listening was that the in these types of activities, the idea is that you follow them through using only the material in the activity itself. So not looking up definitions elsewhere, only looking at the at what you see right here. So I'm going to erase this stuff because we're just going to do it again, and I'll just edit out the beginning. That's fine. Okay. So what you see here to start is this table, and the table is giving us some information that may or may not make any sense to you at all, and it's okay if it doesn't. So some of you, like the people who had lab last week, heard some of these terms in the lab, but others may not. The first column is the just some description, some items, some things. The second column is its classification as an element, compound, homogeneous mixture, or heterogeneous mixture. The third column is its state, and the fourth column is its formula. Now, these symbols may or may not make any sense to you. That's okay. The idea of this activity is to use that information to try to start making some sense of it just because they're given as being related to each other. So let me show you how that works. Again, now that you can hear me. Consider model 1. How does the formula of an element differ from that of a compound? So this question is not meant, what you're not supposed to do here is just look up element and compound and write down some definition from the internet. That's not helpful. That's not getting it into your brain. You should be able to figure this out just from this model, from this table. So we should be able to look at elements and look at compounds, look at their formulas because that's what's given here, and write some differences, write some things that are different about those. So if I'm looking at these formulas, one thing that comes to mind is the elements only have one type of the thing from the periodic table. We can just call it a thing from a periodic table. It's an element symbol. And these have, in this case, two. So I might write a formula for an element has only one type of symbol, and so on, as I just talked about. So that's really the answer. And the point is just that we only got that answer, we only got that information directly from the table. We didn't go look elsewhere. And then number 2 is a very similar question. How can you distinguish elements from compounds based on their chemical formulas? Similar to here, now we just want to broaden and generalize that question. So for all elements and all compounds, how might we come up with an overall rule here to distinguish those? So you can think about that and write something down there. And then for number 3, once again, we're going back to the chart here. I'll use a different color. How does a pure substance, element or compound, differ from a mixture? So now we're going to take our elements and compounds as one group and our mixtures as another group. And maybe we're going to compare the formulas of those. And I think you can see a difference here. The thing that sticks out most for me is this word and. So clearly there's many different types of things in a mixture that can't be described just by one chemical formula. So we might write something like that there. For these introductory questions are these first questions. They're called critical thinking questions on these activities, both this one and the next atoms one. It's not really about getting the right answer. It's about an answer that makes sense based on the data that's there. And then I'll show you where, kind of toward the end, is where it's more important to get the right answer to show that you're learning this stuff. All right. So then we get a little bit of information. Information, of course, is just, you're just supposed to read it. So you read the information and you see matter can be classified by its state, and it's telling you a little bit about some states of matter. So if that's not information that you knew, you can read that there. And it tells you a little bit about those phase labels. So notice up here, it asked you what the meaning of the labels are. It said hypothesize on the meaning of those labels. And then down here, it said, it just tells you what they are. And the reason for that is that a lot of research shows that if you try to come up with these answers on your own, and you try to guess about things, you try to look at data and make conclusions about it, it sticks in your brain a lot better than if you just read the answer and try to remember it. So for all of these, the point is to try on your own and try to work through it with just the data provided, and then get the actual answer kind of afterwards. All right. So same thing here. We get some more information now. The information specifically defines all of these things that we were just working on: element, compound, homogeneous, heterogeneous mixture. And so a standard textbook kind of thing would be to just read this first and then write down the answers to the question. But I really encourage you not to do that, because it'll make a lot more sense and it'll stick in your brain better if you can try it and try to come up with these rules on your own first, and then look at the actual definitions just to kind of cement it and make sure you're not getting any misconceptions. All right, so now we have another model here, some different representations of the water molecule. So you can see the formula H2O or HOH. That kind of gives you a hint as to what that little subscript 2 is going to mean here, right? And then we've got some Lewis structures. We've got where you kind of have lines showing how they're connected at some different angles. Then we have what we call a ball and stick model and a space filling model. All of these are representations of a water molecule. None is more correct than the other. They're used in different situations, and they're all just representations. All right, you can look at some elements. Now for this one, number 8, I am going to kind of give you some extra information here that isn't in here. If you look at the periodic table, and I've got one to show you here. There it is. So you can see here's the periodic table. Normally, if we were in school, it would be nice. I could point up to the wall there, but we'll do what we can here. And you can kind of see these green elements that are, if you can't see green, I'm pointing to it. So it's here, 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 there, and kind of going down the angle. Well, there's a little kind of a stair step pattern that goes down this way, and everything over to the left is a metal, and everything over to the right is a non-metal. So again, it's asking you not to count, but rather just to estimate how many metals and how many non-metals there are. Right, it just says metals, actually. All right. So now it's asking you to kind of figure out some of these ball and stick models. So if you go back up to that model, you should see that in a ball and stick model, each ball represents one atom of a particular type. So in this case, the darkest ones are carbon, then the middle larger ones are oxygen, and then finally hydrogen. I don't know why I lost my pointer here. You can see it, it's really small. Okay, so here, just for an example, we'll do this one together. I see carbon atoms right there and right there. So that tells me there's 2 of them. I'm going to write that as C2. Then I see hydrogens, 1, 2, 3, 4, 5, 6. And then oxygen. The order in which you write the letters doesn't matter. The convention, the kind of standard way to do it is CHON and then other stuff, but you can do it however you want. It's still correct. So you could call that C2OH6. All right, so this one, same kind of thing. The only tricky part here now is what happens when we have these parentheses. So I think you can probably guess what happens there. But if not, look it up or ask me. I'm not going to tell you right now. I want you to take a guess at it and see. All right. And then as we move into, number 3. Yeah, right here, number 3. This is the kind of thing that I really want you to be able to do when you finish this activity. So I want you to be able to be given some sort of a substance and categorize it either as an element, a compound, a homogeneous mixture, or a heterogeneous mixture. So we're going to do a couple together, and then I'll let you do the others on your own, and I'll talk about a couple that maybe are less clear. All right, so a lead weight, we're going to assume this is made only of lead. So we can look at our periodic table and see if we can find lead. Actually, am I covering it up? No, just barely not covering it up. It's right over my shoulder right there. There's lead. It is an element. So if it is an element and it's on the periodic table, then we can pretty clearly say that that is a pure substance and element. Okay, moving on. Let's look at D, air. So air, what is air made of? Now, to figure this out, you may have to do a little bit of digging. You may have to look some stuff up, particularly the components of air. So I will tell you that air is made of, if you don't know, oxygen, nitrogen, water vapor, carbon dioxide, and some other trace gases, but those are the main ones. It's primarily nitrogen. That's what most of air is, and then with some other stuff. So if you know about some of these things, you can look them up also. Oxygen, the formula is O2, nitrogen is N2, water is H2O, carbon dioxide is CO2. So we have that situation like up in the original table where there is multiple different things that are not chemically bound together. And that tells us that this has to be a mixture. If it can't be represented by one formula, either one element or multiple elements together in a formula, then it's a mixture. So now we have to decide, is it homogeneous or heterogeneous? Homogeneous mixture is uniform throughout. Heterogeneous, you can determine the different parts of it. Well, with air, all the different molecules are diffused pretty evenly throughout. We don't have oxygen on this side of the room and nitrogen on this side of the room. So we can pretty confidently call air a homogeneous mixture. All right, and that's how that works. Some of these don't have a clear answer, by the way. And so, for instance, let's look at one of those. I think concrete is one that doesn't have a clear answer. The clear answer part, or the thing that is clear, is I think we can definitely say that this is a mixture. I'm going to let you think about for a second whether it's heterogeneous or homogeneous. If you're here and you're listening, just drop it in the chat what you think, and we'll see. We'll see what everybody thinks. Sorry, I have to disappear for a second. I'll be right back. All right, I'm back. No, nobody wants to play along. We just got a bunch of people watching. All right, that's fine. You can play along later if you want. Okay, So the reason I picked this one is I think either answer could be correct. It depends how you see your concrete. So if you look really close down at the concrete, I don't know how much time you spend on the ground, on the sidewalk or on the street. Hopefully not too much. But if you look at it closely, you'll see that concrete is a mixture of rocks and cement that binds the rock together. That's kind of how it is defined. And from that standpoint, it looks quite heterogeneous. You can see the rocks, you can see the cement. Depending on the road material, like if you look at the road versus a sidewalk, in the road you can often really clearly see the big rocks. In the sidewalk, you have to look pretty close to see the individual rocks. It can look quite homogeneous. So if it's been asphalted, nice and smooth and black, then it maybe looks very homogeneous. So in that case, depending on how you look at it and how you analyze it, it could really fit in either category. The closer you look at it, the more heterogeneous it gets. And that's going to be true for everything except solutions. Solution is another term for heterogeneous or for homogeneous mixture where hold on, I got a question here. Are mixtures also homogeneous because the mixture is consistent throughout? Well, that depends on the mixture. So mixtures can be either homogeneous or heterogeneous. If the mixture is consistent throughout, it is homogeneous. If it is not consistent throughout, then it is heterogeneous. And sometimes how you look at it depends. So what I was saying is a solution, like if you dissolve something in water, you would have to zoom all the way into the molecular level to actually see those differences. So that's going to be homogeneous, absolutely. But other things, whether they're more like suspensions, depending on your vantage point and how you're viewing something, a homogeneous mixture may look heterogeneous as you get closer and closer into it. And you'll get some practice with that in the lab. Some people did that last week, and the rest of you will get to do it this coming week. All right, so that's pretty much it for this worksheet. I will tell you, you don't need to do these last couple. This kind of comes from a textbook where you would use this as a regular class. We're just taking a little bit out of it. So you don't need to do that stuff. But the rest of it is good. And so you'll need to complete that at some point this week and submit to Blackboard. Please let me know if you have questions or if you have trouble completing it. You can send me pictures of your answers or just questions. I do want to make sure that you know how to categorize these things by the end of the week. All right. Any other questions about mixtures? Or if not, then we will move on to atoms. All right, no mixtures questions. Okay. I really like this one. It really helps you process the different names, the different ways that we refer to the particles and how atoms are made up. So in this case, we're going to do the same thing that we did in the previous model. We're going to look at these pictures in the previous activity. We're going to look at these pictures, and we're not going to look things up elsewhere. We're going to see if we can answer these questions based only on what we're given in this particular activity. So we're given these pictures, and we're told that there are some protons, neutrons, electrons, and that this is how we're expressing them. There's some other things given here. There's some complicated symbols. There's some big numbers underneath with AMU. Again, you may not know what any of that means, and that's okay. We're going to figure that out as we go through it. We're given some extra information here about something called isotopes. So we're told that these three things are isotopes, and these things are isotopes. All right. So some of this may sound pretty familiar for you, probably does for most of you. You've probably learned a little bit about atomic structure, about protons, neutrons, and electrons. What I've found over the years is a lot of people have this wrong. Somehow it got twisted up in your head over the years, and it didn't quite come out right. So if you would, kind of put away your previous knowledge about this stuff and try to learn it again fresh, because there may be a chance that something's not right in your head about when you learned it before. And it's not your teacher's fault from before. It's been my experience that uh, sometimes people have these mixed up a little bit, and we're going to try to get it all straightened out right here. Okay, so let's go look at our questions. Look at the schematic diagram for carbon. What do all 3 carbon atoms and ions have in common? So we're just going to go back up to these 3 carbon atoms and ions, which are these 3 here. And we're going to say, what do they all have in common? Well, a couple things, right? They've all got the letter C. They're all called carbon. But that's really where the similarities stop. With one exception, they each have 6 protons. So you'll notice they have different numbers of neutrons, they have different AMUs, they have different of these electrons floating around here. These two have 6, and this one has 7. They have slightly different numbers up here, and we're going to get into all that stuff. But for now, we can just say that they all have 6 protons, and they all have C's in the word carbon. So they all have a C, and they all have 6 protons. What do all 4 hydrogen atoms and ions have in common? What do all magnesium atoms and ions have in common? I'll leave those to you, but I think you can figure them out. All right, and what we're going to find there, all right, fine, we'll just do it together. So the hydrogen atoms all have, and ions all have 1 proton. And the magnesiums all have 12. All right, look at a periodic table. Let's do that. Considering your answers to those questions, what is the significance of the atomic number above each element in the table? So let's look at the ones we talked about, C, H, and Mg. Let's find them in the table here. So I can see C right above my head there, and it is number 6. I can see hydrogen way over to the left. That is number 1. And I can see magnesium also way over on the left. I can't reach that far without going off my screen here, but kind of down and just to the right of hydrogen. And that one is number 12. So we can say, I think pretty clearly, we can see what the significance of atomic number is in this case. That atomic number gives the number of protons. Move that. Okay, there we go. So then looking here, how many protons are in all chlorine atoms? How do you think you can figure that out if it's not given in the model? Well, in this case, we're given a hint here above here. Look at a periodic table. So let's look at a periodic table. I know I said not to use other references, but a periodic table is always there. We assume it's always there. If we were in class, it would always be there. You'll have it for quizzes and exams, whatever. So we can always assume that a periodic table is there. So we look at chlorine, which is just over my head here, and we can see that it is number 17. So we can probably make a pretty good guess that that's going to have 17 protons. And do you think chlorine atoms exist with 18? What do you think? I'll leave that to you. The other thing that's important about these is you have to read the questions because they'll give you some important information. So like for number 7, in a box in the corner of each schematic in Model 1 is the element symbol and the mass number for the atom, superscript on the left side of the element symbol. How is this mass number determined? So let's go back up to that model. And sure enough, yes, we see these symbols and we see the mass numbers on the left. So we want to know how is that determined? And by looking at some of these simpler models and then also the more complicated ones, I think you can see that hydrogen 1 has 1 particle here, hydrogen 2 has 2 particles here, hydrogen 3 has 3 particles here, carbon 12 has 12 particles, carbon 13 has 13, carbon 13 here, 13, and so on. So that should lead you to a conclusion there of what that mass number, where that mass number comes from, or how it's determined, and you can fill that in here. Mass numbers here are, this seems like a very, like an almost too simple question, but that's literally what it's asking. So the mass number here is going to be 37, 238, 12, and 13. Okay. So then we're going to look at the periodic table a little bit. For each element, this is kind of an important distinction, and it's one that's confusing, and often people bring misconceptions into this. So this mass number that we're talking about, this mass of the atom, of an individual atom, is not given on the periodic table. The periodic table gives us the atomic numbers, and then it gives us this other number underneath here. But notice that is generally not a nice even whole number, not even really close to 1 by rounding. And that's because that number is an average. It's an average atomic mass, meaning the average of all of the atoms on Earth based on their abundance. So it's a weighted average. And that number we'll use in some calculations later, but that is not the mass number that we're talking about here. So you have to be given either the number of neutrons or the mass number to be able to figure that out. You can't get it from the periodic table. Okay, this stuff you can kind of go through. And then we get into the end here. So I want to especially highlight right here. This is what I really want you to be able to do from this. So if you're given a symbol with a mass number, or you're given some numbers of protons, neutrons, and electrons, can you figure out the rest? Can you figure out the symbol? Can you figure out the charge? Can you figure out the mass number? Whatever you need to figure out. Can you do that? So this is really kind of, use this as like a test. Can you get all of those, and can you go through those? And to help you with that, I want you to give it a try. So I'm not going to go through it right now, but I want you to please ask me if you have questions about these, or if you are unclear about what should go where. One thing you should note, all of these blanks should be whole numbers. If you've got a decimal in there somewhere, you're doing it wrong. Those should all be whole numbers. We're counting things. We're just counting things. So all whole numbers. Let me know if you're having trouble, or send it to me sometime after the weekend, after this is due, so maybe Monday. I'm going to come back on and go over it again and go through all the answers just to make sure that it's clear. But I want you to try it first and give it your best shot. As with the other one, there's some kind of extra stuff here that you don't actually have to do. So this is where it would have been in a different class. This comes from a different sort of a class, so we're not going to do that. You can look at the metals, nonmetals, semi-metals. You can do that stuff. But the real important stuff here is being able to count subatomic particles. All right. So I think that's it for this stuff this week for the kind of in-class work. There's also going to be an article report. I'm looking through some of the videos and reports from the first round of at-home experiments for the group BO2. They're looking great, and I'm excited to see BO1s next week. And then the following 2 weeks, we'll kind of do the same thing again. So the one group will propose a new at-home experiment, while the other group is doing lab on campus, and then we'll switch. And then 2 weeks after that is when you actually perform the labs. All right. While I'm here, if there are any questions, if you want to put them in the chat or in the Discord, and I can answer them live. Otherwise, of course, you can always send me notes, email me questions, whatever. Anybody got anything you need right now? Oh, all right. Thanks, John. Great. Well, we'll try to do this relatively regularly. Hopefully, it's helpful to work through some of this stuff. And I'll see half of you in a couple days, and the other half of you next week. Stay safe, stay healthy, and enjoy your chemistry. Good night.